Hello everyone, so in this video we're gonna be doing some past paper problems for unit 6. I think I'll do about half of the problems in this entire document, which is about like 20 questions I think. So yeah. Alright, so first question. A molecule of mass m travels at a speed v, hits the wall at a direction perpendicular to the wall. The collision is elastic, where the changes in momentum and in the kinetic energy of the molecule caused by the collision. So recall that momentum, denoted as P, is equal to mass times velocity. So first we can draw a diagram, free body diagram, and our ball is hitting the wall at V, and then afterwards it will go here like that. So we got to calculate the change in momentum. So momentum before here is equal to the mass of the molecule. We don't know it, but we can denote it as m times v, and our kinetic energy is 1/2 mv squared. Afterwards, our momentum here is just going to be m times negative v, because it's going left instead of right, and our kinetic energy is equal to 1/2 m negative v squared. And this just simplifies to 1/2 mv squared, and this simplifies to negative mv. So the change is momentum is going to be the final minus the initial. So this is our final and this is our initial. So it's going to be negative mv minus mv, which is negative 2 mv. In this case, we're actually ignoring the sign. And if we look at the answer choices, we can see that the only one that has a viable answer is C. We don't even have to check the kinetic energy, but it's worth to check that it is 0, because before and after it is still the same. Also, you should note that it is elastic, meaning that kinetic energy does not change, or does not change, is constant throughout the system. Thus, if the collision is elastic, the change in kinetic energy should be 0. Alright, next problem. Which of the following is a statement of the principle of conservation of momentum? Okay. So we have to talk about the conservation of momentum, which states something along the lines of momentum before is equal to the momentum after. And we need some statement that kind of just talks about this in general. So momentum is the product of mass and velocity. This is true, but it's not about conserving the momentum, so it's not A. In elastic collision, momentum is constant. Okay. In this case, this is the definition of an elastic collision, so it's most likely not it. C, the momentum of an isolated system is constant. So this is basically what we're trying to say. When it means that it's constant, it means that the change in momentum is equal to 0. So this is most likely the answer, but we'll check D just to make sure that it doesn't talk about, or it doesn't have a better answer than C. So the force acting on a body is proportional to its rate of change of momentum. So this is actually Newton's second law, I think. that states that F is equal to change in momentum, but it's proportional. So it's like based on time, a factor of time. So this is C. A moving object strikes a stationary object. The collision is inelastic. The objects move off together. Which row shows the possible values of total momentum and total kinetic energy for the system before and after? So yeah. So in this case, the collision is actually inelastic, which means that the sum of momentum before and after is not equal is always equal. In every collision, the momentum is always equal before and after. But the same cannot be said about kinetic energy. I'm blanking. So based on these two informations, we can try and eliminate some answers. So in this case, the total momentum before and momentum after, these are not the same, so we can eliminate that. And we see here the kinetic energy before and kinetic energy after. These are the same, so there's no way this is right. And now we're left with B and C. So this is kind of like a real life example, in my opinion. But if you think about it, if you have a ball and it hits some stationary ball, do you expect both balls to move faster than they were before? In other words, would you expect more movement than previously? That's essentially what B is saying, is that you introduce some type of kinetic energy, but in our system, we have no external force that introduces it. So there's no way that we can get more kinetic energy. Thus, we actually lose kinetic energy in this case, probably due to friction or drag force. So we can do a quick sanity check. So momentum is the same, kinetic energy is not the same, and we decrease our kinetic energy. Yeah. So this question is basically just exemplifying the definition of inelastic. Okay, so I originally did this problem, and I kind of like got lost doing it. So I'm actually gonna redo this. So two balls X and Y are moving towards each other with speeds 5 and 15 meters per second respectively. They make a perfectly elastic head-on collision, and ball Y moves to the right with the speed of 7 meters per second. What is the speed and direction of ball X after the collision? Okay, so we know that it's an elastic collision. So that means that momentum and kinetic energy are conserved. So then we can actually derive two equations, not derive, but like we can use two equations to try and solve for the speed and direction of ball X after the collision. So the first thing we can do is do momentum. So we're gonna say that the mass of this ball is gonna be mx, and the mass of ball Y is gonna be my. So then, and we can also assume that this is the positive direction and this is the negative direction. So for momentum, it's going to be 5 meters per second, the speed multiplied by mx plus 15 times my is equal to mx, and then we can say v of x is our final answer that we're looking for, plus my times 7, because we're going to the right. And I already made a mistake. It's not plus here. It's actually minus because it's negative 15. So then if we try and simplify this a little bit, so 5mx minus 22my, because my here are the same term. So equal to mx v of x. And then we can divide by mx. 5 minus 22 times my over mx is equal to v of x. And then now we have kinetic energy. So then here we have 1/2 times the mass mx times velocity squared. It's going to be 5 squared plus 1/2 my negative 15 squared is equal to mx 1/2 mx vx squared plus 49. Just skip a step. Plus 1/2 my 7 squared. So we can expand out the square terms and multiply by 2, so we get rid of the 1/2s. So then we get 25 mx plus 225 my is equal to mx vx squared plus 49 my. Now we can move this here. Then we get 25 mx plus 176 my is equal to mx vx squared. And then we could divide by mx again. Then we get 25 plus 176 my my divided by mx is equal to vx squared. It's actually kind of messy the way I'm doing it, because it's it should be a subscript, but it looks like it's regular, but these are subscripts. So then we have momentum and kinetic energy. So we got this 5 minus this variable equals vx. And then it turns out we can just say like my over mx is equal to some arbitrary value called r, and we can just solve for r. So then we can say that 5 minus 22r is equal to vx, and then 25 plus 176r is equal to vx squared. And then we can substitute this in to solve for r. So we get 25 plus 176r is equal to 484, I think, r squared. 22 times 5 is 110, multiplied by 2 to get the quadratic value. Plus 5 squared is 25. And you solve for this. And then you get 396r equals 40r. So then r is equal to 0. And r is equal to 396 over 44. You can divide by 11, 36 over 44, and divide by 4 is equal to 9 over 11. So since we know that r is 911, we can plug it in here to get our original equation. And it turns out this becomes 2, this becomes 1. You get 5 minus 18 equals negative 13. Thus, we move 13 meters per second to the left. Which is B. Okay, so this is number 3. Two balls X and Y are supported by long strings as shown in figure 3.1. The balls are each pulled back and pulled towards each other. When the balls collide at the position shown in 3.1, the strings are vertical, the balls rebound in opposite directions. Figure 3.2 shows data for X and Y during this collision. The positive direction is horizontal and to the right. Use a conservation of linear momentum to determine the mass of Y. Okay, so we have to use conservation of momentum in this case. So in this case, m of x times v of x before. So in this case, it's going to be 4.5 plus my that we don't know. My negative 2.8 is equal to mx negative 2. That's final. Sorry, this graph is kind of confusing. Times 1.4, and then you plug in things that we do know. So we have 4.5 mx minus 2.8 my is equal to 0.05 because it's kilograms, plus m times negative 2.8 is equal to 0.05 negative 1.8 plus 1.4 my, or in this case it's going to be m. So we can move this on this side and move this on that side. So then we get 6.3 times 0.05 is equal to 4.2 times mass. And we divide this by 4.2. This gets canceled out. So then it's about 1.5 of it. So it's going to be 75 grams. State and explain whether this collision is elastic. So for the collision to be elastic, we need the kinetic energy before and after to be the same. So you can actually try and calculate it. So kinetic energy of the x would be, or it's like 1/2 50 grams, but it should be kilograms. 0.05 4.5 squared plus 1/2 0.075, as I found in the previous part. 2.8 squared, negative 2.8 squared is equal to 1/2 0.05 1.8 squared plus 1/2 times 0.075 times 1.4 squared. And you can see if they're actually equal or not, but I'll just save the calculation and say that they're not. So kinetic energy is not conserved. Thus collision is inelastic. Use Newton's second and third laws to explain why the magnitude of the change in momentum of each ball is the same. So the second, oh, that's large. So the second and third laws. So the second one is F is equal to ma. And then the third law is something along the lines of equal and opposite reaction force. So we have to use both of these laws. Since it's 3 marks, it should be something like 3 statements, 2 including the second and third laws, and then a final like actual answer. So we have to make sure that the magnitude change. So since by the Newton's third law, there's an equal and opposite reaction, the magnitude should always be the same. So we can just write that out. Since I spelled that wrong. Newton's third law says that for every action there's an equal and opposite reaction. Opposite reaction, thus magnitude is the same. As for Newton's second law, the magnitude is the same because the acceleration is the same, I assume. Or more specifically, force is proportional to change in momentum. Thus, that's why magnitude is also the same, because if the force is the same, then so is like the change in momentum. So then the last mark is just saying, the time of collision is also the same for both ball X and Y. Thus, the general average force they experience is also the same. Thus, the change in momentum is the same. So it's kind of like, it's kind of like that. Mark 1, Mark 2, Mark 3. Okay, a gas molecule with mass 6.64 times 10 to the negative 27th power and the speed of blah. The molecule collides normally with the flat surface and rebounds with the same speed. Calculate the change in momentum of the molecule. So the change in momentum will just be P final minus P initial. So our P final, we'll assume that this is positive and this would be negative. But generally, since it's only in change, I think it should generally be positive no matter what. So for P of F, it's going to be 6.64 times 10 to the negative 27th kg times 125 meters per second minus the same thing times 10 to the negative 27 times 125. But this is going to be negative in this case, so then 2 negatives make a positive. So it's going to be 6.4 times 10 to the negative 27 kg times 250 meters per second. And you can just calculate this real quick. which is gonna be 1.66 times 10 to the negative 23rd kg meters per second, or ns, so it's gonna be 1.66 times 10 to the negative 23rd. In this case, it's gonna be 3 sig figs, I think. Even though this should also be 3. You can and you should actually do 1.7 just being safe. But generally AICE should give you the mark regardless. It's usually a range anyway. Okay. So which statement about a ball that strikes a tennis racket and rebalances is always correct? The total kinetic energy is conserved. There's nothing talking about like an elastic versus elastic collision, so we can't really assume anything about the kinetic energy about it. And not every collision is elastic, and we want it to be always correct. So that's why the kinetic energy, you can't like make any assumption on it. Or a statement, sorry. The total momentum of the ball is conserved. Not necessarily, because the ball still experiences some change, and thus some other objects will also experience a change in momentum. This is not necessarily true. So then we're left with D, which is saying the total momentum of the system is conserved. So this kind of makes sense, because when the ball hits the racket and it gets hit back, the racket, if it's inelastic or in any collision, the racket should also experience some type of force. But obviously it's more massive than the ball, so it doesn't move as much. Two identical spheres X and Y approach each other with the speed shown and undergo head-on elastic collision. What are the velocities of the spheres after the collision? Okay, so without loss of generality, we can say that our ball masses is equal to 1 kg. So then, so we can use momentum equation, and our kinetic energy equation. I should highlight that is elastic, so we can say that the kinetic energy before and after are the same. So for momentum, our mass is 1 times 4 plus, actually I should write units. Generally you should write your units, because there are some problems where it's so confusing that if your units are not the same at the end, you know that you will make a mistake. So 1 kg, and then we'll denote the thing, the final velocity of x as v of x, and then same thing of y plus 1 kg v of y. So then we get 2 at s is equal to v of x plus vy, and we can do kinetic energy. So 1/2 times m, which is just going to be 1. 4 squared for ms negative 1 squared plus 1/2 1 kg times negative 2 meters squared meters per second squared is equal to bx squared. I left out the negative 1 because it's not very useful. So then we get something along the lines of 1/2 times 16 plus 1/2 times 4 is equal to 1/2 times vx squared plus vy squared. And then we get 20 is equal to vx squared plus vy squared. This is also going to be in like joules, but we can say that we have these two equations here, and then we can actually solve for each one. So this becomes vy equals 2 minus vx, and then we can substitute this to here. So we got 20 is equal to vx squared plus vx squared minus 4vx plus 4 x minus 4 vx minus 16 is equal to 0. And then we can simplify this. So then, sorry, there's kind of no space moment. So vx minus 4, factor this, vx minus plus 2 is equal to 0. So then in this case, v of x equals 4 and negative 2. But the thing is though, our initial collision is that it's already 4. And we know that most likely it's going to change velocity anyways. So our solution of 4 is kind of extraneous. So then our velocity of x would be negative 2. And negative 2 would be to the left. So then it would be c, because we have our negative 2 to the left. Or 2 meters per second to the left. But yeah. Also, we know that the 4 is extraneous because it's saying that it's going in a positive direction at 4 meters per second. But we actually have no answer choice that uses that, basically. If you take this negative 2 and plug it in for this equation right here, you'll get that v of y is also equal to 4 to the right. Alright, so next question. Two equal masses x and y are moving towards each other on a frictionless air track as shown. The masses make an elastic collision like this. Which row gives possible velocities for the two masses after the collision? So they're asking for possible velocities, but we're not given. Oh, we're actually given that they're two equal masses. So then we kind of just do momentum, I think. So let's say with a loss of generality, mass of x and y is 1 kg. So then I can make 50 times 1 plus 30, or minus 30, sorry. 30 times 1 is equal to v of x times 1 plus v of y. So then 20 is equal to v of x plus v of y. So I can kind of try and see where this kind of makes sense. So then if we look at A, see that this is 0 and this is 20 meters to the right. So this is a possible answer. Because 20 meters to the right is positive 20 in momentum. 10 meters to the right and 10 centimeters squared Sorry, my words. So we get 10 and 10 to the right, so then that's going to be 20 to the right. For C, so then this is possible. For C is 20 centimeters per second to the left. So that's actually negative 20, so there's no way that makes sense. And then 30 centimeters to the left, 50 centimeters to the right. So if you add these up, it'll be 20. So we're left with A, B, and D. So our next one is kinetic energy. So I don't want to skip too much, but 50 squared plus 1/2 times 1 times 30 squared is equal to 1/2 Vx squared plus 1/2 Vy squared. So we can multiply by 2, and then we get something like this. Here's the round 3400. So this is actually really exciting. And it turns out that if we look at A, the kinetic energy of this will be around 400. The kinetic energy of this will be 200, because if we square this and then add them, so then our only correct answer is actually D. So this is actually kind of like really similar to the previous problem here. But this is actually really mathematical. If you want to think about it conceptually, if two identical objects collide, then they will swap velocities. I assume, pretty sure that's correct. But yeah. I'm sure one can actually prove that. But that's out of scope of this little tutoring session. So which statement is correct with reference to perfectly elastic collisions between two bodies? Okay, so in this case, we're gonna have to try and read these things. Neither total momentum nor total kinetic energy needs to be conserved. That's obviously false, because in our perfectly elastic collision systems, our total momentum is usually always conserved. Total momentum and total energy are conserved, but total kinetic energy may be changed. Total kinetic energy cannot change. And this last one is also false. Because it says that total momentum is conserved only if the two bodies have equal masses, but that's not the case, because in previous examples, when we went over this ball and a racket, these two don't have the same amount of mass, but even then the total momentum is conserved. So then we're left with D. Which statement about a perfectly elastic collision between two bodies in an isolated system is correct? So that should actually really jump out at you, because we literally just went, this is similar to the last question. So total momentum and total kinetic energy are conserved, and this is just the same idea with different words. Ooh, okay. All right. So a particle of mass m traveling with speed u collides with a stationary particle of mass m. The velocities of two particles before and after the collision are shown. Which vector diagram correctly shows a momenta before and after the collision? So So the first question is this elastic or inelastic? And then we can see that it doesn't really matter because in either collisions, momentum is conserved. So when we show that is before and after are the same, that means that we have to show that the momentum of before collision is equal to this. But we have to use it using vectors. So let's look at the answer choices to get some ideas of what it might look like. So A here, MU is going right, and in every other one, MU is also going right. So if we look at the diagram of the first one, we can see that the momentum in this case is just MU plus M times 0. Thus, it's just MU. And there's no angle to it. So it's kind of just MU. And that should be the initial then. And then now we have to look at the after collision to make sure that it's actually correct. And in conservation of momentum is conserved in both x direction and y direction. So we have to look for angles that make sense, kind of. I don't know if that makes sense. But generally, what I'm trying to say is that the vertical component of this, let's say this is A, the vertical component of this is B. That means A plus B is equal to 0. So then it's like sine of beta times the momentum plus sine of alpha times big M, actually, U over 3 is equal to 0. So basically these have to cancel out. We have to choose the right angles in the right directions because these directions are weird. Okay, so generally our direction should move right and up or something similar to that. This is because we have to show that they're equal and not that they cancel out to each other to equal to 0. So for example, I'm just saying words, but in C here, not that it's the right answer, but you can see that our initial momentum is actually going right, and then it says that we're going backwards to 0, which means that our objects actually didn't move at all, or they're just like negative each other, so that doesn't really make sense. So it can't be C, and it can't be D, because this is also the same idea of going direction left and up to the left. Because we're not trying to cancel out the momentum, we're trying to show that they're equal. So then we have to kind of look at A and B, and the only thing that's really different are their angles. So I don't know if we look at this diagram here. I kind of wrote this out, but sine of beta times sine of beta actually matches with small m. So in this case, we look here, and wow, this is actually really close. Because this shows that sine of beta is this is the vertical component going down. So in this case, it should be B. A should also work because if you draw a parallel line here, this is also A right here, which is similar to the A like this. I hope that kind of makes sense. But generally, you have to just digest everything that they're giving you and break it up into smaller components, kind of. um, just see differences. The thing with MCQs is that you can look at the answer choices and then make inferences based on answer choices to kind of like get the answer without knowing every concept, basically. All right. So two spheres approach each other along the same line. Their speeds are u1 and u2 before they collide. After the collision, the spheres separate with speeds v1 and v2 in the directions shown. The collision is perfectly elastic. Which equation must be must be correct? Okay. So they don't actually tell us the mass of the spheres. But it seemingly looks like it's actually equal in mass. Let's look at D. U plus 1 plus U plus 2 is equal to V2 minus V1. Not necessarily. I don't think that's right. And we have to try to find why it's incorrect. And I'm guessing that we can use the actual equation for conservation of momentum. For example, like we get u1 minus u2 times the mass of each one, I guess, mass x, mass y equals mass x, v1 plus my going right is v2. And then it turns out that it's actually like right here, I think. This is exactly what we're looking for, except that the masses are a bit different. But we know that our masses are positive, so I guess they're negligible. It would be different if it was just momentum, but who knows. Alright, so a ball falls vertically onto a horizontal ground and rebounds as shown. Before and after, the ball has momentum p downwards just before hitting the ground. After rebounding, the ball leaves the ground with momentum p2 upwards. The ball is in contact with the ground for 0.02 seconds. During this interval, an average resultant force of 25 newtons acts on the ball. What is the possible combination of values for p1 and p2? So, you can actually recall an equation. Generally, we're going to use the equation of F is equal to change in momentum over change in time. This is not too hard to see why, because the units of this is kg ms negative 2, and the momentum is kg times velocity, right? So ms negative 1 divided by s, so then minus 1 is minus 2, so then this is true. So we can just plug in our values. So 25 newtons is equal to change in P over 0.020 seconds. And then we can multiply by 0.02. Then we get 0.5, I think, 0.50 newtons per second is equal to change in P. Remember that change in P is like P2 minus P1. So then, and S, so then, it turns out that it's either A or D, because it's not that they add up to 50. Wait, I have to be careful here, because direction does matter in this case. So I have to be a little bit careful here. So P2 is P final. So this is mass times velocity. This minus is part of the change. mass times negative velocity 2. So then it will become P2 plus P1, I think, because it's negative. So in this case, actually, no, it's not, because we can assume that P is already negative anyway, so it's going to be P1 anyway. So in this case, it should be A. Okay, I low-key lied. I was right the first time. So it turns out that since P is going down, P1 is going down, it's going to be adding it. So this is equal to 50 newtons per second. And it's kind of like assumed that you, when you go up, you're actually like kind of like losing your momentum. You're going up with a smaller amount of momentum. So it's actually going to be C in this case, because this is increasing and this is decreasing. A ball of mass 150 grams is at rest on a horizontal floor. As shown, calculate the magnitude of the normal contact force from the floor acting on the ball. Okay. So since it's not moving, we actually have a downward force and an upward force, and this is downward force is going to be mg, F normal. So then mg would be 0.15 kg times 9.81 meters negative 2 meters squared negative 2. This is equal to F normal. Could we do this calculation? And we got 1.5. Explain your working in I. So this has to be an old question. But gravity and normal force are equal because acceleration is equal to 0. You can kind of further explain this by saying that since acceleration is equal to 0, the force that is the resultant force that is exerting on the ball is also equal to 0. So then the gravity and the force, the two existing forces actually on the ball, have to be equal to each other or 0. Not equal to each other, equal in magnitude but in opposite directions. So they add up to equal to 0. The ball is now lifted above the ground and dropped so that it falls vertically as shown in figure 3.2. Just before contact with the ball has a velocity of 6.2. The ball bounces up from the floor, and its velocity just after losing contact with the floor is 2.5 meters upwards. Balls in contact with the floor for 0.12 seconds. So state Newton's second law of motion. So force is proportional to change in momentum. And let's see if this is actually right. Yes, so this is fine. So now calculate the resultant force on the ball when it is contact with the floor. So we just said that force is proportional to the change in momentum, and that specifically that factor is based on time. So delta just means changing. So the force is equal to change in momentum. Our momentum of this final is 2.5. What is the mass? 0.15. 0.15 minus negative 6.2 times 0.15 over change in time, which is 0.12. And then go ahead and calculate that. This is going to be 8.7 times 0.15 divided by 8.12. And it's going to be 11 newtons. And then it's upwards. This is because the ball falls down and then it goes up, so the direction of the force has to go up. Explain whether linear momentum is conserved during the collision of the ball to the floor. Yes, it is conserved. It's conserved because there's no outer force slash that system is isolated or closed, sorry, is closed. So yeah, I think I'm gonna stop here for part 1.